So last time we met, we were going through the continuum of intermolecular forces. We started off with the weakest intermolecular forces. We've worked through dipole-dipole interactions. And so now, along the intermolecular forces, we're at the strongest of those intermolecular forces. So hydrogen bonds are not bonds in the sense of covalent bonds or ionic bonds. They're intermolecular forces. So there's weak attractive forces between two different molecules. They're a special case of dipole-dipole interactions, and that special case is that they have to have certain atoms involved in covalent bonds, things resulting in very strong dipoles. So we need something very electronegative bonded to a hydrogen. So if we think about the most electronegative things, we're up in the top right corner of the periodic table. So we're in the top right corner with fluorine, with oxygen, with nitrogen, all very electronegative. If they're bound to a hydrogen, they pull very strongly on the electrons from a hydrogen. And so that creates a very strong dipole. So hydrogen bonding is really just a case of a very strong dipole. So hydrogen bonding can occur within a pure substance. So two different molecules within a pure substance. So if we think about water being a pure substance, there's millions and billions of water molecules. Two water molecules can form a hydrogen bond. So when we talk about that hydrogen bond, we were talking about these dashes, right? So not an actual bond like a full-on solid line, but these little dots saying dot, dot, dot. There's a weak attraction here. The attraction is between the lone pair on one molecule and the hydrogen on the other. It's between the delta negative on one molecule and the delta positive on another molecule. So hydrogen bonding is not these covalent bonds that you see within a molecule. Hydrogen bonding can only happen between two different molecules. So that's an example with a pure substance. But it's not pure substances that we're going to come across, right? We learned about mixtures in Gen Chem 1. And when it comes to mixtures, we're talking about mixing two pure substances. So in the case of two different substances, we're looking again for there to be that strong dipole on one of the molecules. We're looking for a oxygen, nitrogen, fluorine bound to a hydrogen so that we create that strong dipole. Now we have a partial positive on the hydrogen. And so if there's a lone pair somewhere else, particularly on an oxygen or a nitrogen, it's going to be able to attract weakly, intermolecular force, that hydrogen on that other molecule. So in this instance, what we've set up is a water molecule. We already know that a water molecule is a polar molecule. It has a delta plus because an oxygen is pulling on the electrons on that hydrogen. So we also have another molecule floating around in this mixture. And when these two molecules get near each other, they're attracted to each other. They're attracted to each other because this oxygen, if you recall, has two lone pairs on it. They're not drawn in there until I just drew them in. Oxygen likes to make two bonds, have two lone pairs, so there's a lone pair over here that can be attracted to that other hydrogen. So between two molecules that are different types of molecules, we still need to have those same criteria. On one molecule, I've got to have an oxygen, nitrogen, or fluorine that's bonded covalently to a hydrogen. And then on another molecule, I need to have a lone pair. That lone pair on a delta negative side of a molecule is going to be attracted to the delta positive on that second molecule. And so again, the hydrogen bond, it's not all these covalent bonds. None of these are hydrogen bonds. The hydrogen bond is between these two molecules. So applications, what are we going to ask you to do with this? We're going to give you a series of molecules. We're going to practice some in this class. We're also going to consider what would happen if this popped up on your homework, or what would happen if it popped up in the quiz. Which of the following pure substances are capable of dipole-dipole interactions? So they're saying you need to have two molecules. So let's go ahead and do A. A is methane. 1 carbon, 4 hydrogens. We learned how to draw Lewis structures. You may have drawn them until you were blue in the face. You may remember carbon likes to make 4 bonds. Hydrogens only make 1 bond. And so this is going to have a structure with the carbon in the middle, hydrogens around the outside. That's 1 molecule. I need to have 2 molecules in order to have intermolecular forces. So in a pure substance, the second molecule is the same thing. So a carbon-hydrogen covalent bond is between 2 different things with 2 different electronegativities. But does it count as a polar bond? No. The difference in electronegativity is 0.4 or below. So this is the one case where you're going to see 2 different atoms bound to each other, and it still gets to be nonpolar. So I have nonpolar bonds. I have 2 nonpolar molecules. So this is not capable of dipole-dipole interactions. Nonpolar bonds, nonpolar molecules. CO2. Do we remember the structure of CO2? We're going to have a carbon in the middle, oxygens on either side. These oxygens have lone pairs. You can imagine we have 2 of these things now. Is a carbon-oxygen bond a polar bond? It's based on electronegativity, and so we're thinking that the thing that's most electronegative, the oxygen, is going to pull unequally on those electrons. The electrons are going to move away from the carbon toward the oxygen, and so those are our dipoles. We're going to have a partial negative and a partial positive, a partial negative and a partial positive. So those bonds are polar, but is this a polar molecule? It's not a polar molecule because the dipoles are pointing in equal and opposite directions, so they cancel out. So if this is a nonpolar molecule, we cannot have dipole-dipole interactions. Skipping down to D, we're going to put the sulfur in the middle. We are going to have an F on the top and bottom. We are going to have a flat plane of fluorines. So a flat surface with 1 fluorine pointed up and 1 fluorine pointed down. Is a sulfur-fluorine bond polar? So we're thinking about electronegativities. They're kind of in the same area on the periodic table. We just have to be above 0.4 difference in electronegativity. So pretty much, if you see 2 things bound to each other that are different elements, and it's not carbon and hydrogen, we should be thinking it'll be polar. Because for the most part, the differences are going to be 0.4 or above. So if every one of these bonds is polar, is this a polar molecule? No, it is not a polar molecule because we've got a dipole pointed straight up and pointed straight down. Those cancel out. And then we have 4 dipoles pointed at the 4 corners of a square. So those are going to cancel each other out because they're all equal in opposite direction. So it's a nonpolar molecule. So this one also is not going to be able to do dipole-dipole interactions.
So one of the fluorines is positive, one negative. That's why it cancels out?
No, so if we were to draw the dipoles in here, fluorine is going to be the most electronegative, so the electrons are going to move this way. It's also going to move this way. So that's straight up and straight down, completely opposite. They cancel out. They're the same magnitude because it's the same type of bond. Opposite direction, so they cancel. If you think about a square, these things are really this one and this one are pointed in opposite directions. Same magnitude, opposite directions, they cancel. Same thing here. Same thing here. They cancel. So overall, this molecule is not polar. So when it bumps into another molecule, it can do London dispersion, but it can't do dipole-dipole. So then we move on to the last one. Carbon likes to be in the middle. Carbon likes to make 4 bonds. Oxygen likes to be on the outside if it needs to, likes to make 2 bonds, 2 lone pairs. Hydrogens only make single bonds. So if we put that carbon in the middle and we try to satisfy all those rules, we're going to have a molecule like this. Again, we drew Lewis structures. You can go back over the rules for writing those Lewis structures. But at this point, you're going to start to hopefully see some trends as to what carbon likes to do, what oxygen likes to do, and it'll help you rearrange these molecules. Is a carbon-hydrogen bond polar? No, we established that, right? 0.4 or less, difference in electronegativity, so that carbon-hydrogen bonds on the left are not polar. Is a carbon-oxygen bond polar? Yes, difference in electronegativity. Remember we said oxygen's very electronegative. So that means we're going to have a dipole pointed at the oxygen. There's only one dipole. There's not another dipole for it to cancel out. So this molecule has a slightly positive side and a slightly negative side. When it bumps into another molecule of the same type, they're going to orient themselves such that the negative side is going to be near the positive, or the positive is going to be near the negative. So what I mean by that is that if another one of these came along, we would end up with the carbon-hydrogen, this side being slightly partial positive on the carbon, double bond to an oxygen, this would be the partial negative side. We would have a dipole-dipole interaction between the partial negative and the partial positive. So the oxygen on one molecule would be slightly attracted to the carbon on another molecule because of those dipoles, because of the partial charges. So these types of problems require you to be able to draw Lewis structures, to be able to think about the types of bonds, to think about the polarity of those bonds and whether they cancel out in a symmetrical molecule, to give you an overall polar molecule or an overall nonpolar molecule. Nonpolar molecules are going to be able to do dispersion forces, and that's it. Polar molecules can do dispersion forces because everybody can do dispersion forces. They can do dipole-dipole interactions. They can only do the special case of dipole-dipole interactions, which is hydrogen bonds, if you've got a hydrogen covalently bound to an oxygen, a nitrogen, or a fluorine. So you're going to have to run through these molecules and think about the types of interactions that are happening. So this is another set. This is going to be your participation activity. You're welcome to just tell me in the discussion board, A, B, C, D. You're welcome to take a picture if you want to. It's going to be a chapter 10, right? Participation activity. Is this number 1 or number 2? So this is the first of potentially 2 in chapter 10. And so this slide is already in your notes, right? It's already part of the slide deck. It's just not yellow in that slide deck. So you coming to class or you watching the video, it's going to allow you to see that this is highlighted yellow, and I'm looking for your answer. You're going to have to work through that same process that I just did on the previous slide for these other molecules. Lewis structure, types of bonds, overall molecules, polar or nonpolar, what types of intermolecular forces of attraction are exhibited by those molecules. All right, so we don't want to just talk about intermolecular forces. We want to talk about the consequences of those intermolecular forces. We want to know there's some utility in discussing intermolecular forces. So intermolecular forces are the attractive forces between different molecules. In a pure substance, they're different molecules that have the exact same structure, but they're different molecules. So when we think about melting and boiling, we're talking about forming or disrupting the interactions between molecules, right? If you have a solid and you want to melt it into a liquid, you need to disrupt the intermolecular forces between those molecules in order to allow them to break down a crystalline structure of a solid and go into more of a fluid structure of a liquid. If you think about boiling, you have a liquid. Molecules in that liquid are touching each other and they're attracted to each other, so they're not flying off into the gas phase. But if you disrupt those interactions, now you're going to allow things to escape into the gas phase. That's the boiling point, the point at which things that are in the liquid phase start to go into the gas phase. So in a solid, you have the strongest intermolecular forces. In a gas, you have the weakest intermolecular forces. So we talked about the halogens. in group 7. Small molar mass for fluorine and chlorine, weak intermolecular forces, only dispersion forces. Those exist as a gas at room temperature because they have weak intermolecular forces. As those diatomic gases get bigger and bigger in molecular weight, as we move into bromine, now we can end up with a liquid at room temperature. Bigger molecular mass, bigger surface area, more dispersion forces, enough to keep them together as a liquid. Iodine, even bigger, diatomic molecules, more surface area in contact with other molecules, forms a solid at room temperature. So those are going to be the strongest intermolecular forces. So they're all dispersion forces, but the surface area changes, the molar mass changes, and so the interactions, the attraction gets stronger as we get bigger and go down the periodic table. So just based on the boiling points, so of these boiling points, all in the same scale, all in Kelvin, which would you predict has the largest intermolecular forces? Something that's a solid at room temperature has a lot of intermolecular forces. You're going to have to put heat into it to turn it into a liquid before you can ever turn it into a gas. So if we're talking about boiling points, the thing that had the highest intermolecular forces, you're going to have to break down twice. Break it into a liquid, then break it into a gas. You'll have to put in more energy. It's going to have a higher melting point and a higher boiling point. So there's a relationship between the intermolecular forces and the ability for molecules in a liquid to go into the gas phase in order to go from a liquid to a vapor. So vapor pressure is another way of describing that transition from a liquid to a gas, from a liquid to a vapor. So formally, vapor pressure is known as the pressure exerted by the vapor that's in equilibrium with a liquid in a closed container at a given temperature. So let's break that down a little bit. We have to have a closed container. That closed container has a liquid in it. If you sealed that container at time zero, all the molecules are in the liquid phase. So these are going to be my X's. These are just molecules that are all in the liquid phase. At time final, I'm going to have some number of those molecules in the gas phase and some in the liquid phase. So equilibrium will be reached, an equilibrium at which some are in the gas phase, some are in the liquid phase. The overall ratio, the overall number of those molecules does not change because now we're at equilibrium. So just like we would reach equilibrium in our thermal systems, right, where something is getting cooler or something's getting hotter, they meet in the middle. In this sealed container, they're going to meet in the middle. They're going to meet in the middle in which some are in the water phase or the liquid phase, some are going to be in the vapor gas phase. So the ratio of the molecules in the gas phase to the molecules in the liquid phase is going to depend upon the substance. So water, for instance, has a specific value associated with its vapor pressure. That value is talking about how many molecules are in the gas phase versus how many are in the liquid phase. If you sealed up a container of rubbing alcohol instead of water, an equilibrium would be established, but we would have a different ratio of molecules in the gas phase to the liquid phase of that rubbing alcohol. And that's because rubbing alcohol, isopropyl alcohol, has a different vapor pressure as a property of that compound. So vapor pressure is specific to different substances. They all have different values, just like everybody has a different freezing point and everything else. So if the liquid that we're talking about, if that substance has high intermolecular forces, it's going to be able to keep more molecules in the liquid phase. It's going to be able to recapture anything that escapes into the gas phase. So water does hydrogen bonding. That's one of the reasons why your glass of water doesn't completely evaporate as it sits there in front of you. It's because there's not a lot of pressure for those molecules to jump into the gas phase. Water is perfectly happy to hold on to those molecules in the liquid phase. Now, alcohols are more volatile. Gasoline is more volatile. We talk about the fumes that come off of these things. They're going to evaporate faster because the intermolecular forces are weaker in the liquid phase, which allows molecules to escape into the gas phase. If you sealed one of these containers, they would have a different vapor pressure than water, a different ratio of molecules in the gas phase relative to the liquid phase. So if the molecules are able to escape easily, we're going to say that that liquid has a high vapor pressure. That's because many molecules go into the vapor. So in the example we're talking about with water, and say gasoline, water is going to have a lower vapor pressure compared to the gasoline. More molecules of the gasoline are going to try to go into the vapor phase. When you seal that container, the volume of gasoline is going to start off pretty high for the liquid. Given enough time, you'll actually probably see a shrinkage in the amount of liquid because a lot went into the gas. But water, you're not going to see that volume of liquid change that much because not a lot is going to go into the gas phase inside of that container. So boiling point is another way of describing the likelihood that something is going to go from the liquid phase into the vapor phase, to go from the liquid phase into the gas phase. When the vapor pressure of that liquid is the same atmospheric pressure, boiling occurs. So if you think about this, if you've got that liquid, atmospheric pressure is pressing down with 1 atmosphere of pressure. If this liquid has a vapor pressure of 0.5 atmospheres, atmospheric pressure is winning, right? It's pushing down on the surface of that liquid. It's letting those liquid molecules stay in the liquid phase. At the point where the vapor pressure continues to climb and becomes, say, 1.5 atmospheres, now it's winning. Now it's pushing those molecules out of the liquid phase and into the atmosphere. And so some liquids, say like gasoline, are going to start off with a vapor pressure that's greater than the atmospheric pressure. Gasoline disappears very quickly before your eyes because of its vapor pressure. But for liquids such as water, which have a lower vapor pressure than atmospheric, we can change the vapor pressure by increasing the temperature. So if you heat that pot of water, you're going to increase the vapor pressure of the water in the pot until it is up around 1 atmosphere, at which point it can start vaporizing, at which point it can start going into the gas phase. So we can actually modulate the vapor pressure by changing the heat. So if you run across something where they're talking about the normal boiling point of something other than water, that normal part, the boiling part, is referring to this idea that we typically see around 1 atmosphere of pressure pushing down on a liquid. What's the point, temperature-wise, at which we're able to get the vapor pressure of the liquid to equal the vapor pressure of the atmosphere so that those gas molecules can start escaping? So that allows us to graph this information. A pressure versus temperature curve can be drawn for any compound. So water, for instance, at a temperature of 0, has a pressure that's very, very low. And that makes sense, right? Really cold water doesn't want to boil. Really cold water has no motivation to let those water molecules escape into the gas phase. But if you start to increase the temperature, now we're getting up around 40 degrees, now we're starting to increase the pressure a little bit, continue to increase, now we're increasing the pressure, still not boiling, we get up to 100 degrees Celsius, this is the point at which we're going to start to boil. We've now increased the pressure to the point where we are comparable to atmospheric pressure. Now we're going to allow the water molecules to escape. So any of these liquids, ethyl ether, ethyl alcohol, can be measured what is the vapor pressure at all of these different temperatures. And differences in intermolecular forces can explain why some of these have certain curves. So given a graph like this, we can ask questions. What would the pressure have to be for water to boil at 60 degrees Celsius? So in this case, if we go to 60 degrees Celsius, we're here, it only has a pressure of around, say, 25, right? Just ballparking it, has a pressure of 25. So the vapor pressure is 25. We would need to have an atmospheric pressure that was also around 25, in this case, kilopascals, in order for that to boil. So we just go up to the line, and then we go across. So for instance, in outer space, the pressure is very low, right? So you watch those movies, and if liquid gets anywhere near a vacuum of space, which has no pressure, it just starts vaporizing. So that's the kind of thing we're doing here. We're saying that at a certain temperature, how low can the pressure be in the atmosphere in order for this thing just to start boiling? We could also ask, at what temperature does ethyl alcohol boil at when the pressure is 70 kilopascals? So we go up here to 70 kilopascals. Say we're around here. We're just going to go across until we get to ethyl alcohol. And so at this point, we would come back down and we would say, okay, 70 degrees Celsius. So around 70 degrees Celsius, we could get ethyl alcohol to boil, given this pressure. So it's just a matter of finding whichever tick mark on whichever axis they give you, tracing up to the curve, cutting across to the other axis, and getting that number out. Based on this graph, what can we say about the intermolecular forces of ethylene glycol? So if 105, if this area is where water boils, this curve needs to be way up here for us to talk about it boiling at room temperature. But it is so far down there that we're going to have to go out to temperatures, 400 Celsius, in order to get that line to ever come up. So ethylene glycol is actually a really long molecule. It's very viscous if you have a macroscopic amount of it. And it's viscous because of all the really long molecules having a lot of dispersion forces between each other. So this flat line over here is suggestive of the ethylene glycol having strong intermolecular forces. Another way to think about that is to think, okay, water has pretty strong intermolecular forces, but what about these alcohols? Alcohols typically evaporate faster than water, right? That's why they put essential oils and alcohols and stuff together. There's alcohols in perfumes and stuff. So the weaker intermolecular forces on the left side of this graph, they're going to boil at lower temperatures. Ether was one of those things that they used in medicine back in the day, like chloroform and stuff, right? Where they would put it on something and make you breathe it and you pass out. It's volatile. If it's volatile, has a low boiling point, weak intermolecular forces. So we've got the weak intermolecular forces over here and the strong over here. All right? Right, so for the molecules over on the right side, you're having to go to higher temperatures for it to boil. Because at higher temperatures, you're able to increase the vapor pressure, but it's just going to take a while. And so something else that might appear down here might be something like motor oil, right? It takes a really high temperature for that to ever boil, right? So we can think about more and more viscous things like honey and stuff like that, further and further to the right. So calculating vapor pressure. So it's nice that they graphed that for us. They must have had some data to graph. But how can we calculate vapor pressure? We can use the Clausius-Clapeyron equation. Part of the reason why we do the math practice homework in Cengage is because we're going to start to do weird things, like use natural logs. We're going to use e raised to things. And so while I'm not looking for you to get 100 on that, I'm looking for you to attempt it and realize that you do or do not know where to find those buttons on your calculator. Go learn a little bit more about it. Talk to one of your math professors if needed. So the vapor pressure can be calculated using this equation. The negative delta H vapor is the enthalpy of vaporization for a liquid. So that's the kind of information you can get in a table where somebody has just provided a bunch of delta H vaporizations. So if you know what liquid you have, you go look it up, and that can be used as part of the solution to find out what the vapor pressure is. R is the universal gas constant, so it needs to be the 8.3145 joules per mole Kelvin. We've talked about R can be different things in Gen Chem 1, depending upon the units of pressure that you had. In this case, there's only one version of R that we want to use, and it's the 8.3145. T is the temperature. A is a constant that depends on the substance. So in this equation, we actually have to go to a table to look up a lot of information. We've got to figure out what the A is. We need to go look up the enthalpy of vaporization for that substance. And so there's actually a full version of the equation. And if you did the math homework, you realize there's a relationship between the natural log, which is the ln, and that E. And so to get rid of the E, we need to apply the natural log to our equations. That simplifies as this equation. So the most commonly used form is this form. And we could have gone through the mathematical steps to translate that other thing into this form. Take it from me. This is not actually a math class. And so we just want to use the most useful form of the equation. So in this, we're looking for things at time 1 and things at time 2. We're looking for the pressure in the beginning and the temperature in the beginning. That would be your P1 and your T1. We're looking for your pressure at time 2 and your temperature at time 2. So this is one of those before and after type problems. So a typical problem that uses this equation is something like this from your textbook, where they want you to come up with the enthalpy of vaporization. They're not interested in you calculating the pressure. They want to know what is the enthalpy of vaporization for this compound. So isooctane is something that goes into gasoline. We know that it has an appreciable vapor pressure because gasoline is one of the things we talked about evaporating pretty quickly. So they give us one temperature, and they give us a pressure. kPa is kilopascals. And then they give us a second temperature. Now we raise the temperature, and we find out that the pressure has gone up. So they want you to use this information to estimate the enthalpy of vaporization. The enthalpy of vaporization is this number. So we're going to plug in everything we know and then try to rearrange to solve for that. So what do we know? We know P1 because I said that we started at 10 kilopascals. We know T1 because we started at 34 degrees Celsius. Our temperature needs to be in Kelvin. So we're going to add our degrees Celsius to 273, or if you're being specific, 273.15, and that converts your degrees Celsius into Kelvin. We also know the second time point. We know that the second pressure is 100 kilopascals. We know the second temperature is 98.8. Again, we're going to take 98.8, add it to our conversion factor to get to Kelvin. If we remember our rules for sig figs, when we do addition, we're looking for the least number of decimal places. Looks like the 10th place in both of these. If you had just used 273, then it would have been the ones place. So it's helpful to use the 0.15, 273.15, because that's going to give you more significant digits to play with in your answers. So now it's just a matter of plugging that information in, remembering that there's only one specific value for R that we want to use. So we're going to have the natural log of 100 divided by 10 on one side. We're solving for the heat of vaporization, so we're just going to leave that as an x or a variable. We're going to divide the heat of vaporization by R. Can't do much with that right this second, but we can plug in values for T1 and T2 and actually get a number out. So this is 1 over T1 minus 1 over T2. So we can simplify that. It's going to be a really small number because it's 1 over a big number, minus 1 over a big number. So we end up with this long string of numbers in our calculator. It's division. So we're expecting 4 sig figs in both of those numbers. Then when you subtract them, we have to think about the least number of decimal places. I'm keeping track of my sig figs over here. I can go ahead and simplify the natural log of 10 into a number. 3 sig figs there, 3 sig figs here. I'm going to divide both sides by this number. 2.3025 divided by that really small number should give me a big number because I'm dividing by a really small number. Tracking my sig figs, there were 4 sig figs on the right, there were 3 sig figs on the left. My answer from division step is going to be 3 sig figs. Now I've got heat of vaporization on one side divided by R. I'm just going to multiply both sides by R so that I can get rid of this 8.3145. Still going to have 3 sig figs in my final answer. I now have a number that's equal to the delta H of vaporization. I'm going to round that 6. Is going to tell me to round up. So 33,800 joules per mole, or 33.8 kilojoules per mole. So it's algebra from the point that we plugged everything in. And then, of course, keeping track of our sig figs so our final answer makes sense. So in your textbook, they work the examples out with commentary. You'll also have this video if you're looking to refresh yourself on that. So what we've been describing is that transition between a liquid and a gas. That's a physical change. Physical changes are reversible because we're just talking about changing the phase of matter. So if we go from that liquid to a gas, that's vaporization. We want those liquid molecules to become a vapor. If we want those gas molecules to turn back into a liquid, that's condensation. If you have a cold object and you have water vapor in the air, when that water vapor comes and touches that cold object, it's going to turn back into a liquid. That's condensation. If we want to go from a liquid to a solid, we're going to freeze. You've definitely heard of that before. If we want to go from a solid to a liquid, we're melting. It's also known as fusion. In Gen Chem 1 labs, we like to do, actually it's 1151, we like to do a lab where we actually do sublimation, where we take solid iodine and we get it hot, and it turns into a purple vapor, and you never see it as a liquid. It just goes directly from a solid to a gas. So that's sublimation. If you put another beaker or you put a watch glass or something on top of that vapor, when it touches that colder glass object, it'll turn back into a solid. So again, you never see it as a liquid. It would go straight from a gas to a solid, and we call that deposition. So different words to describe which 2 phases of matter are we talking about, and which direction are we going in. Some of the terms you've heard, some of them you might be able to figure out, some of them we have to explain. So there are energies associated with each one of these transitions. If there's an enthalpy associated with going from a liquid to a gas, there's also an enthalpy associated with going from a gas to a liquid. For a given substance, that enthalpy change is the exact same magnitude, it's just the opposite sign. So if it takes 100 kilojoules of energy to make something go from a liquid to a gas, for that same substance to go from a gas to a liquid, it's going to be negative 100 kilojoules. Okay? So the sign changed because it would be exothermic in one direction and endothermic in the other direction. It takes the same amount of energy, it's just are you putting it in or are you taking it out? So you have to put endothermic next to boiling, right? You boil water, you put in energy. That energy allows the water molecules to escape. They have energy in them now, kinetic energy. In order for them to condense, they have to slow down. In order for them to slow down, they have to give up some of that kinetic energy. They're going to give up the same amount of energy that they accepted in the first place, right? So we would consider condensation to be exothermic. That water has to give off that heat, has to give up that energy in order to become a liquid again. So we can go around this triangle and consider any of these processes. In order for a liquid to freeze, the higher energy liquid molecules are going to have to give up energy in order to form that crystalline solid. Well, if I'm giving up energy, I'm exothermic. I have a negative delta H. If you want to melt a solid, you're going to have to put energy in. That's going to be endothermic. I'm going to have a positive delta H. It takes the same amount of energy to thaw something as to freeze it. It's just a difference of the sign. The magnitude is the same. For sublimation and deposition, same type of process. If I have a solid and I want to excite it to the point where I can turn it into a gas, which is this sublimation going on right here, I'm going to have to put energy into that. That's going to be endothermic. If I take gas molecules with a lot of energy and I ask them to recondense, which is what's happening at the top up here, if I'm asking them to go from high energy gas molecules to locked into a solid crystalline structure where they're not allowed to vibrate very much, that's going to require them to give off energy. That's going to be exothermic. So we ought to be able to rationalize what's happening to those molecules in considering what the sign is going to be on these different enthalpies. And if we're talking about enthalpy, we're still talking about a state function. The energy required to go from a solid directly to a gas is the same as if you first did a step where you went from a solid to a liquid and then a liquid to a gas. So if we're talking about an ice cube, trying to get it to go directly to a gas, that would take a certain amount of energy. But if we took the energy required to get it to go from a solid to a liquid and then added it together with the energy required to go from a liquid to a gas, we would find out that those energies would be equal. It doesn't matter the number of steps. So when we think about that in terms of a heating curve, we can break out those different steps. We could compare a heating curve going directly from a solid to a gas to that same curve for going solid to liquid, liquid to gas. We should come up with the same energy value for either of those because it's a state function. But an interesting thing happens in these heating curves. So on the x-axis, we have the amount of heat added. So we're adding heat this whole time. More and more heat has been added as you go from the left to the right. The temperature of your substance is over here on the y-axis. So if you have a really cold ice cube and you add heat to that ice cube, it's still going to be an ice cube for a while. It might go from an ice cube that was minus 20 degrees to an ice cube that's now minus 10 degrees, but it's still an ice cube. So if you have a solid object, the first amount of heat that you add to it is going to get it up to its melting point. And so the first leg of our journey is increasing the temperature of our solid. At the point that you get to the melting point, all of the extra heat that you're going to add is going to break down that crystalline solid. So the temperature of your solid is not going to change. All you're going to be doing is converting solid into liquid. You're breaking the intermolecular forces between those molecules. So the temperature doesn't increase. You kind of have a plateau here where you're not going to see a change in the temperature. At the point that every one of those molecules is now in the liquid phase, adding heat is going to heat up the temperature of the liquid. You're going to go from a very cold liquid to a very hot liquid. And so if we're dealing with water, we have to go all the way from 0 degrees Celsius all the way up to 100 degrees. Now when we get to 100 degrees, now we're at the boiling point. Now that we're at the boiling point, all the heat that you add is going to start to break the intermolecular forces between those liquid water molecules. So you get another flattening of the curve, and you're going to add heat as long as you have to until everything gets into the gas phase. And that might take a while. If you boiled water, you can usually leave it alone and come back to it, and there's still water in there. So that's the reason why your boiling pot of water tops out at around 100 degrees. You're not going to come back and find your pasta's burned by the water, because the water's not going to get hotter than its boiling point. Is that your observation after cooking macaroni noodles, right? Now you can burn something in oil, right? Because oil has a boiling point well above 100 degrees. So you can get that material burnt because it's so much higher in temperature. But water is not going to go above that 100. So at the point that everything's in the gas phase, if you trapped it and continued to heat that gas, you would be able to increase the temperature of that steam. Okay, so there's distinct phases on a heating curve related to what's going on with our material. Are we heating it but keeping the phase the same? Or are we breaking down the intermolecular forces within that phase, allowing it to move on to the next phase? So if we think about this term in terms of energy, we could calculate the energy to get it to 100 degrees. We would need to know the energy associated with that phase transition. We could add that to the energy required to get it up to 100. There's another pocket of energy that we'd have to account for the phase transition, and then if we got that up to 120 degrees Celsius, according to those markers, that would be another piece of energy. So if they wanted to know how much energy do you have to add to get solid water to go from minus 10 degrees up to a gas at 120 degrees, there would actually be 1, 2, 3, 4, 5 legs of this journey, 5 different energies that we would have to add together. So we can use a phase diagram to describe any material. We just talked about water, what happens when you get water to go from a solid liquid to a gas. Any substance has some transition between a solid liquid and a gas. The transitions, generally speaking, are going to depend upon the pressure and the temperature. At a high enough pressure, you can get gases to be liquids, right? Have you ever been behind one of those trucks on the interstate with all those canisters of compressed gas? Or tried to get a canister of helium or something for a birthday party? They're heavy as all get out because it's liquid in there, and they have to have very thick metal to account for all the pressure that they've put on that gas. So as pressure rises, we form solids. Diamonds form because we take carbon, we put it under such extreme pressures that we turn it into this really hard solid. So as pressure rises, pressure's over here on the y-axis, we should be thinking about solids. So in our phase diagram, this is actually the region that corresponds with solids. Now, if we take any solid and we heat it up enough, we raise the temperature enough, we should expect that we should be able to turn that into a gas, right? If you heat an ice cube long enough, you're going to turn it into gas particles. So at high enough temperatures, we should be able to get things to go into the gas phase. So this region of our graph is for gases. Anybody want to wager a guess what's in the middle of the Y? Liquids. So all 3 phases of matter are depicted here. If you have a gas at a certain temperature, say we're here, and you raise the pressure, now we're going to go up. We can get that gas to turn into a liquid. And that's the idea behind those compressed canisters of gases. Now, if you keep increasing the pressure, technically, you can cross this boundary. When you cross that boundary, now you're up in the solids. So if you think about carbon dioxide, for instance, at a low enough temperature, at a high enough pressure, it can form dry ice. It can be that solid. So the boundaries between these areas are the transitions between phases. So this is the liquid to gas or gas to liquid transition. This line is the solid to liquid transition. That means for some things, for all things actually, there is a transition where we can go straight from a solid to a gas. And that's because these are the quadrants that are touching along that line. And so that does work for carbon dioxide. Get it low enough, you're expecting to be able to see it as a solid. Under low pressure, atmospheric pressure, it'll turn back into a gas. And that's why dry ice looks like it's smoking. So on this phase diagram, there's another area that we didn't draw in, and that is the SCF area. We'll talk about that in a minute. And there's 2 points that we need to know about on these diagrams. One of them is the triple point. The triple point is where 3 lines intersect. So 3 lines coming together should help us remember that we're talking about a triple point. So at that triple point, if you have a beaker of that material at the correct temperature and pressure corresponding with the triple point, you are likely to have all 3 phases of matter at the exact same time. It will be a solid, liquid, and a gas in that container at the same time. They will be in an equilibrium. And at that triple point, if you lower the pressure, it will turn into a gas. All right, because we're talking about lowering the pressure, and so that's going to drop it into the gas area. No option for a liquid at that point. The critical point is up here by the SCF area. So what the critical point means is that after you get to a certain temperature, you're not going to be able to get that gas to go back into being a liquid. Doesn't matter how much pressure you apply, it is so hot you cannot get it to condense back into a liquid. You can apply all the pressure in the world and we can't get it to go back into being a gas. So that's why that line kind of ends. So at the critical point, the critical temperature says above that temperature I can't liquefy the gas. The critical pressure is the last pressure that would have been able to liquefy that gas. So at the critical point, which happens between liquid and gas, we have both a critical temperature and a critical pressure. So what is the SCF? That's the point at which we have a supercritical fluid. So S for super, C for critical, F for fluid. If you take a liquid and you put it in a sealed container and heat that container, eventually you will be able to reach a temperature at which the liquid will become a gas. At that point, we can reach a phase of matter that is the supercritical fluid. It has some properties that are like a liquid and some properties that are like a gas. You can think about it as a very dense gas. Like a gas, it's going to fill up the entire container that you put it in. Like a liquid, it's going to be more dense than you would expect for that gas if you just establish an equilibrium with the vapor pressure. And like a liquid, you can actually get things to dissolve in that gas. Which is kind of crazy, right? You think you dissolve salt in liquid water, but you could actually dissolve powdered salt in this supercritical fluid, in this gas. And it would stay in that gas. So the last question I want to leave you with, I hope you go research this and we have a conversation about it next time, is I got an iPhone several years ago. It's waterproof, but you read the instructions and it says don't put it in the dishwasher. Relative to what we're talking about here, why should I not put my waterproof electronics in a dishwasher? take a peek, see what the internet says, talk to your friends, call Verizon, I don't know. We'll pick it up next time.